In this lesson, we're going to look at functions. Now, functions are relationships between two quantities that express some sort of dependency. Let's look at some examples. First of all, we want to decide whether A is a function of B is a function of A, or neither. And as a first example, we're going to let A represent a positive integer smaller than 100, and B represent the number of divisors of A. We need to decide whether A depends on B. Now, if A is a positive integer smaller than 100 and B is the number of divisors, A is not a function of B. Now, let's decide if B is a function of A. Since B is the number of divisors and A is the number, B does depend on what number we're talking about. So we can say B is a function of A. Let's look at another example of the same type. Decide whether A is a function of B is a function of A, or neither. And in this case, we have let A represent the age of a United States citizen, and B represent the number of days since his or her birth. As far as A being a function of B, we can say in this case A is a function of B, because age does depend on the number of days since his or her birth, a person's birth. But B, we'll say, is not a function of A, specifically because of the word days. The number of days does not depend on your age. It depends on exactly your birth date. Let's try a third example of the same type. Decide whether A is a function of B is a function of A, or neither. And this time we have let A represent the age of a United States citizen and B represent his or her annual income. Well, there is no functional relationship here at all. A is not a function of B. Let me write that down. A is not a function of B, and I can also say B is not a function of A in that particular example. Let's continue by looking at a more formal definition of a function. A function is a set of ordered pairs in which no two ordered pairs have the same first coordinate and different second coordinates. No two ordered pairs have the same first coordinate and different second coordinates. We often call the first coordinate the independent variable, and the second coordinate, I should point here, second coordinate the dependent variable. There is a way to use this definition to identify functions from their graphs. What we use is something called the vertical line test. A graph is the graph of a function if and only if there is no vertical line that crosses the graph more than once. And so this particular graph here at the left is not a function because this vertical line that's drawn, and many vertical lines, will touch the graph more than once. And notice that that means somewhere there are ordered pairs with the same first coordinate but different second coordinates. For that reason, this second graph is also not a function. Notice a vertical line might touch it more than once. But the third graph is a function because any vertical line will only touch that graph once. Here are some more examples. For each of these, we want to determine whether each relation is a function. And first we see the relation, the set of ordered pairs, that contains 1, 3, 2, 3, and 4, 9. This is a function because each first coordinate only corresponds to one second coordinate. 1 only goes with 3. 2 only goes with 3. 2 doesn't go with something else, for example. In the second set of ordered pairs, we contain 9, negative 3, 9, 3, 4, 2, and 0, 0. This is not a function, and we see that by looking at the first two ordered pairs, which both have the same first coordinate but different second coordinates. And in our third relation, we have two related items, quantity and price. We have quantities 1 through 5 at a price of $9.40 and 5 through 10 at a price of $8.75. This is also not a function specifically because of the quantity 5, which is paired with a price of $9.40 as well as with a price of $8.75. Now functions can also be written as equations. For example, here we want to determine whether each equation defines y as a function of x. In the first equation we have x equals 3y minus 9. Since we want to decide whether y is a function of x, let's solve it for y, first by adding 9 to get 3y as x plus 9, and then multiplying through by 1/3 to get y as 1/3 x plus 3. Now this is a function, this is y as a function of x if each x corresponds to only one y. And if you look at the nature of this equation, no matter, or as I put an individual x into this equation, I'm only going to get one y for each of those values. So this is a function. Now the next equation we have says x squared equals y squared. We could solve for y as we did in the first case, but another method we might use is to try to choose some values. For example, if x is -3, well, -3 squared is 9, and so one value of y that corresponds to x being -3 is 3. But if x is -3, y could also be -3, and that would make this a true statement. 9 equals 9. And so since both of these ordered pairs with first coordinate -3 satisfy the equation is not a function. Finally, we have the equation y cubed equals x. Since this is a cube, not a square, and we noticed a problem with a square in the equation, I'm going to think that this is a function of x and consider different values of x and what kind of y values would correspond. For example, if x is 8, y could be 2, but if x is 8, y could only be 2, not some other value in addition. So we can conclude that this is a function relationship also. Now, there are other kinds of ordered pairs other than functions. There are relations, and we've used that word quite a bit. And for each relation, the set of first coordinates is called a domain, and the set of second coordinates is called the range. Let's look at some examples and use that terminology. What we want to do is state the domain and range of each relation, and state whether each relation is a function. Now, a relation, as I mentioned, or as you might know, is a set of ordered pairs. So they're all relations. We want to decide if they are this special kind of relation called a function, and state their domain and range. Starting with the first relation, the domain, I'll just use a D for domain, is the set of first coordinates, which I can write as the set containing the number -1 and the number 3. Those are the only two unique first coordinates. The range is the set of second coordinates, and that will contain 1, 9, and -9, all the unique second coordinates. Now I want to determine if this first relation is a function. I see that it is not a function because the coordinate 3, the first coordinate 3, corresponds to two different second coordinates, so it is not a function. Well, here's our second relation, set of ordered pairs. As far as the domain goes, I need to know what x's I can substitute into this and then be able to take the square root of in the set of real numbers. So I want the 2x minus 1 in the end, as a result, to be greater than or equal to 0. Solving this inequality by adding 1 and dividing by 2, I see that x needs to be greater than or equal to 1/2. Well, that's the domain. The domain is the set of x's such that x is greater than or equal to 1/2. Now the range is the set of second coordinates, or y values. Since y is equal to this square root, the positive square root, we say that the range is the set of y's such that y is greater than or equal to 0, or positive numbers. Now, is this a function or not? Well, each individual x, when substituted into here and simplified and its square root taken, will give us a unique value of y, so this is a function. In our third example, x is equal to the absolute value of y. So the domain is the set of x's, and since x is equal to the absolute value of something, it's going to be positive numbers, so we say the domain is numbers greater than or equal to 0. Now the range is the set of y values. Anything can be put into an absolute value, so we'll say that the range is all real numbers, and I'll write that as an interval from negative infinity to infinity, or you could write all real numbers. Now, is this a function? For some particular x, is there more than one y that would correspond to that? And the answer to that is yes, which makes this not a function. For example, if x were 2, y could be either 2 or negative 2. So one first coordinate corresponds to two different second coordinates. Well, let's continue by looking at a special notation that we use to describe functions. The notation f parentheses x is read the value of f at x, or simply f of x. So y and f of x are both symbols for the value of the second coordinate when the first coordinate is x. For example, the function y equals square root 2x minus 1 can be written as f of x equals square root 2x minus 1, because y is the same thing as f of x, or y equals f of x. Well, what we do is use function notation within problems, and here's one example of how we might. What we want to do is find each of the following for the function f of x equals square root 2x minus 1. First of all, f of 5. Well, what we use this notation to tell us is f operates on x and does this to it, so f is supposed to operate on 5 and do to it what it does to x. In other words, replace the x with a 5. 2 times 5 minus 1 is the square root of 10 minus 1, or 9, which is 3. So we conclude that f of 5 is 3. The second example says find f of a plus 2, and we work this exactly the same way, replacing the x in the function with the quantity a plus 2 to get the square root of 2 times a plus 2 minus 1. Now let's clean up the information inside the square root by distributing a 2 and then combining the 4 and the negative 1 to get 2a plus 3 in the square root. So we say f of a plus 2 is equal to the square root of 2a plus 3. Let's try another example. Given that f of x is x squared minus 2 and g of x is 2x minus 3, find and simplify each of the following expressions. First of all, we want to find and simplify g of x plus h. That means replace every x in the function g with the quantity x plus h. Well, here's the function g. Replace this with x plus h to get 2 times x plus h minus 3. And now clean up our answer by distributing a 2. If it were possible to combine like terms, I would do so, but there aren't any in that particular example. Secondly, I want to use function notation and find f of g of x. Well, g of x is the function 2x minus 3, so this means find f of the quantity 2x minus 3. So everywhere there is an x in the function f, put the quantity 2x minus 3. Well, here's function f. For this x, put 2x minus 3 to get 2x minus 3 squared minus 2. Well, we should simplify by squaring 2x minus 3, which means to multiply it by itself. And using the distributive property or FOIL method, we get 4x squared minus 6x is minus 12x. Negative 3 times negative 3 is 9. And combining these like terms, the result is 4x squared minus 12x plus 7. So f of g of x for these two functions is this new function 4x squared minus 12x plus 7. Well, now it's your turn to try a problem. Here's what I'd like you to try. Let f of x be 3x squared minus x, g of x be 4x minus 2, and k of x equal the absolute value of x plus 3. Find the following. Find g of negative 1, find f of x plus h, and find f of k of negative 4. Pause the video and try this problem and then restart it when you're ready to check your work. Well, let's see how you did. First, we want to find g of negative 1. That means everywhere there's an x in function g, replace the x with a negative 1. There's function g. We will find 4 times negative 1 minus 2, which is negative 4 minus 2, or negative 6. Next, we want to find f of x plus h. That means for each x in the function f, replace it with x plus h. Well, there's function f. So each x is replaced by the quantity x plus h, which gives us 3 times x plus h squared minus the quantity x plus h. And don't forget the parentheses on the quantity being subtracted. Now to simplify this, we're going to square x plus h, multiply it by itself to get x squared plus 2xh plus h squared, as well as distribute a negative. And finally distribute a 3 to get 3x squared plus 6xh plus 3h squared minus x minus h. If there were any like terms, I would combine them, but there aren't. So this is the result of f of x plus h. And finally, we want to find f of k of negative 4. And I'm going to work down for the first step. K of negative 4 means to take this particular function and replace the x with negative 4. So I want f of the absolute value of negative 4 plus 3, which is the function k with the x replaced by a negative 4. Now let me simplify what's inside here. This is f of the absolute value of negative 1, which is f of 1, and that's where I continue from. To find f of 1, I replace each x in function f with the number 1, and remember that this is function f. That'll be 3 times 1 squared minus 1, or 3 times 1 minus 1, which is 2. Well, let's continue, but I wanted to find something called average rate of change. If the ordered pair x1, y1 and the ordered pair x2, y2 are two ordered pairs of a function, we defined the average rate of change of the function as x varies from x1 to x2 as the quantity y2 minus y1 over x2 minus x1. This is exactly the slope of the line from one of these ordered pairs to the other. Let's work an example. A wallpaper company specializing in antique reproductions charges $560 for 40 yards of hand silk-screened wallpaper and $780 for 60 yards of the same paper. Find the average rate of change of the cost as the length varies from 40 to 60 yards. So what we're going to do, or what the information that we're going to pull from this example, is the number of yards and dollars as ordered pairs. In the order, yards as the first coordinate, dollars as the second. So if you look back at that example, you'll see that 40 yards corresponds to $560, and I'll write the dollar sign in just for the moment, and 60 yards corresponds to $780. What I'm going to do first is plot those 2 points to get an idea of what this average rate of change is all about. I'm going to plot the point 40, 560, approximately there, and 60, 780, approximately there. And what I'm looking for is the average rate of change of the cost as the yards vary from 40 to 60. Notice what happens if I draw a horizontal and vertical line until they meet and find this particular change, which is going to be the $780 minus 560, and this particular change, which is 60 minus 40. Keep those quantities in mind as we find this average rate of change. If you look back at the formula, what we're going to do is subtract the y-coordinates, 780 minus 560, and put the result over the difference in the x-coordinates subtracted in the same order. Now 780 minus 560 is 220 divided by 20, and if we reduce this, this is 11, and we would attach units to our answer as $11 per yard, or we could write $11 per yard with sort of a fraction bar. Well, this average rate of change is related to something called the difference quotient. Let me give you that definition now. The expression f of x plus h minus f of x, all of that over h, is called a difference quotient. The difference quotient is the average rate of change, there's the connection, between 2 points that are labeled x f of x and x plus h f of x plus h. So instead of x1, y1, x2, y2, we're using slightly different notation. In calculus, it's often necessary to find and simplify the difference quotient for a function. So there's a reason for finding it. Let's try it out. Let's find the difference quotient for each function and simplify it. And we'll start with the function f of x equals 3x plus 5. Well, if you look back at the difference quotient, the first thing I need is the function evaluated at x plus h. That looks like 3 times x plus h plus 5. So it's that same function with the x replaced by x plus h. I subtract from that the function evaluated at x, or the function itself, and I'm going to divide all of that by h once I've simplified the numerator. Well, let's multiply out the numerator. We have 3x plus 3h plus 5, distributing a negative, minus 3x minus 5, all of that over h. Now the 3x's add to 0, and 5 minus 5 is 0, so the numerator is 3h over h, and simplifying the h's, the result is 3. Let's work part B on a separate sheet of paper. Here we have the function f of x equals square root x plus 2, and we want to find that difference quotient. So again, the first thing we have to do is evaluate the function at x plus h, which is going to look like the square root of x plus h plus 2. Subtract from that the function itself and divide that by h. Now, to simplify this particular difference quotient, what we do is we rationalize the numerator. So take the numerator as it is, square root x plus h plus 2 minus square root x plus 2, and multiply it by square root x plus h plus 2 plus square root x plus 2. But as with any fraction, this is over h, recall. We can't just multiply the numerator by some quantity, so we multiply the numerator and the denominator by the same quantity. So we're multiplying by 1. That's a 2. Now what happens in the numerator as we multiply things out is we end up with the square root of x plus h plus 2 squared minus the square root of x plus 2 squared. Let me write it that way as an intermediate step. We end up with the first quantity squared minus the second, sort of a difference of 2 squares. And in the denominator, intentionally, I am not going to distribute the h plus square root x plus 2. Back to the numerator, squaring a square root undoes the square root, so I end up with x plus h plus 2 minus the quantity x plus 2 all over the same denominator. And if I distribute the negative, I can see that the x's will add to 0, and 2 minus 2 is 0, so I'll end up with h in the numerator over h times the square root of x plus h plus 2 plus square root of x plus 2. Now the reason I didn't distribute the h is because I knew I would at this point want to simplify the factor of h to end up with 1 over square root of x plus h plus 2 plus square root x plus 2. In this lesson we've done a number of things with functions. Be sure to work lots of exercises from your textbook for practice.